Okay, so third time was not the charm. I'm going to try this again. One of these days, I'll get good internet and I'll get my editing skills up to snuff. But so please do bear with me. I'm trying to get these out on time, and this is a lot on top of my already busy schedule. So welcome to week 4 Soil Tech with Tattoo Sadhu. We're going to get into some pretty nerdy territory today. It's nothing particularly hard, third grade math, but if this isn't your thing, you can skip this one. It's done for you on your soil tests, but we're going to actually go over how you actually measure or quantify CEC and base saturation percentages and why that's important. If you're allergic to math and chemistry, just follow along for the high points. You can skip the math, and definitely something you don't have to know how to do. But I just figured for most folks, understanding the process, kind of maybe demystifying what's going on in the labs would help with people's understanding and maybe translate into a tool that could help your cultivation. So keep in mind that soil tests for manufactured substrates like we use in indoor cannabis cultivation, that CEC number is not as accurate as it would be on an in situ or field soil test. We've always got plenty of organic matter and lots of exchange sites. But this can give you an inflated CEC when measured in a lab, and if that's confusing, hopefully last week's video could shine a little light on that. If this is already starting to sound confusing, check out the previous videos, and I highly recommend reading Michael Estera's The Ideal Soil Volume 2.0 to get a good understanding of these concepts. CEC is one of the most important for us growers. Soil properties, and it's heavily influenced by soil composition. We talked about that, I think, the week before or the week even before that. Sand, silt, and clay make up your soil, and along with air and water and a very small organic fraction. But that sand, silt, and clay really determines your CEC for the most part. And so the higher your clay content and compost, but the higher your clay, the higher your CEC is going to be. It's expressed as total charge, not a mass or volumetric measurement, but CEC is the potential to hold positively charged ions, called cations, to negatively charged attachment or docking sites on clay surfaces. And that's expressed as milliequivalents or megs. There's also exchange with roots and organic matter and that kind of stuff, but we're focused on the clay, and that's where your cation exchange capacity is measured. It's the summation of all your cations, both acidic and basic or alkaline cations. And so charge and pH, acidity or basicity, are not the same thing. So you can have a basic cation with a positive charge that's going to drive pH up, calcium, magnesium, potassium, sodium. And you can have acidic cations with a positive charge that will attach to negative sites but will drive your pH down. Iron, manganese, hydrogen, aluminum, ammonium, those would all be in that camp. So low CEC just has low CEC soil has relatively fewer attachment sites for positively charged ions, cations, than a high CEC soil would. Um, Again, this is just measuring for potential to hold ions to fertility. It doesn't mean that the fertility exists in the first place. So think of the CEC as like, this is how big your room is, and then base saturation is going to tell you how much is in your room. So that's why these two numbers are important. So you can have a high CEC and low EC, or soluble salts, or just think of it as fertility. You could have high CEC, the ability, the potential. You had a big room, but you could have an empty room with no fertility in it. So high CEC does not mean that everything is already dialed in. We want to see what's actually in the room now, and then CEC would inform us on how to feed. So CEC informs of your strategy for feeding. And so a really high CEC, you would want to do infrequent applications at higher rates, where if you've got sand and a low CEC, you would want to do more frequent applications but at much lower rates. And again, that comes back to sand, silt, and clay. As the clay percentage goes up, so does your CEC. So we've got a CEC metric which tells us the potential to hold cations, and how do we figure out what's actually being held, how much fertility is actually in there. So we want to determine how much of our CEC is occupied, so we need to know what our base saturation is. Excuse me. This metric is used to determine the feeding strategies we just alluded to. Base saturation is simply the percentage of CEC occupied by base cations. Stands to reason that acid saturation, or exchangeable acidity, would be the percentage of CEC occupied by your acid cations. So base saturation percentage is just all your base cations, calcium, magnesium, potassium, sodium, divided by CEC, and this increases with pH. And these two factors are really tightly related. So as your acidic cations, hydrogen and aluminum, are replaced by basic cations over time, you'll be raising the pH. And that's why those weathered soils we've talked about have lower pHs, because they've got the hydrogen and aluminum in them. And so, again, this is, I'm kind of beating a dead horse, but CEC is not indicative of high or low base cation saturation. CEC just tells you the potential, how big is your storage locker. Base saturation is going to give you an idea of how much fertility is actually held by that potential charge, so how much is in your storage locker. You can also look at your CEC as opposed to base saturation. You can look at it as individual ions. So like, what's your calcium saturation percentage? You can look at that in a similar fashion, looking at individual ions instead of the summation of your base cations. So this is something that calcium number is something that a lot of field growers look at. You can do the same thing with potassium or magnesium. Most growers traditionally pay attention to that calcium number and then set their targets from accepted calcium to magnesium to potassium ratios. Calcium to magnesium ratios are usually 3-to-1 up to 7-to-1. Like a lot of cannabis growers, I'm more of a 5-to-1, just kind of a safe intermediate range. We do see with these high output LEDs a lot more stress on magnesium, and so 5-to-1 seems to work a little bit better than 7-to-1 in a lot of cases. Calcium to potassium is often inverted. Some folks will run a 1-to-1. Most growers like myself run a 1-to-2 or a 1-to-3 calcium to potassium. I'm pretty aggressive with the potassium. And so we want to figure out how much of our exchange sites are actually occupied by our base cations. Again, that's calcium, magnesium, potassium, and one we don't like, sodium. Field growers and row crop farmers pay really close attention to this. Again, they have to be, when you've got acreage, you have to be very judicious about your inputs. It can get really expensive, and so they need to be very precise about this. And so calcium saturation percentage, we would just take calcium, divide it by CEC, just like we divided base saturation by CEC for a base saturation percentage. CEC is measured in milliequivalents, or more precisely, milliequivalents per 100 grams of oven-dried soil. So this is our charge to mass relationship. And again, charge is more useful than mass when we're discussing CEC. I know I've mentioned that a bunch of times, but just want that to really stick. Calculating the CEC is pretty simple. So how do we go from mass, parts per million, on your soil test of cations to a milliequivalent of CEC? The lab we use is Logan Labs. So you just want to pick a lab and stick with them. They'll use different protocols, different SOPs, different extraction pHs on their extraction solutions, and so numbers from one lab to the next will be different. Where the numbers at that lab will be accurate and stay accurate over time, but you just want to pick a lab and stick with them, and we like working with Logan a lot. So the CEC is just the summation of both your basic and your acidic cations. You're going to need to look at a periodic table. This is just my nerdy mouse pad. Compliments of Tad, because he knows I'm a dork. And there's lots of information on here that's really valuable for us. And so, right over here, you can see calcium, potassium. Let's see here. Yeah, calcium, potassium, magnesium, and sodium. So here are your base cations. If you take a closer look, you'll see that calcium, all of these will have a charge. You can also see I've been working in the garden. It's super dirty nails, so apologies there. It's a occupational hazard. But you can see I have a charge, 2 plus, and I have a weight, 40 grams per mole of calcium. And so I have both a charge and an atomic weight, and that's really important for my next step in figuring out these metrics. And so for the next step, we want to take these base cations, calcium, magnesium, potassium, and sodium. We've got their atomic weights from our periodic table, and we've got their valence charge. And the valence charge is just the number of electrons in the outermost, most active electron shell. And so if we divide our atomic weights by our valence charge, we're going to get what is called our gram equivalent weight. And that's these numbers right here. Okay, and so we can ignore this last part. Sorry, I'm backwards here with my hand, but we can ignore this last part for a second. So this helps us, if we've got the weight and the valence charge, we can come up with a gram equivalent. And so now, to make these numbers line up and make sense, we've got to take these gram equivalent weights and convert them to milliequivalents. So we're going to divide equivalents by 1,000 milliequivalents per equivalence. So the equivalents are going to cancel out, and we're going to have 1,000 milliequivalents. So now we have to adjust the milliequivalents per 100 grams of oven-dried soil, because that's our metric, right? It's not 1,000 mechs, it's 1,000 mechs per 100 grams. So that's simple. We just divide 1,000 by 100, and then our multiplier is 10. And why that's important is you take that multiplier and multiply that times the 10 times your gram equivalent weight, and now we have milliequivalents per 100 grams of soil. So now we're in business. Now we have a metric that we can use to figure out our CEC and our base saturation. And so now we've got these numbers, and so let's dive into an example. I've just made up some numbers here as though you were looking at a soil test. And so calcium, magnesium, potassium, and sodium, I just put down some random numbers. These numbers could be off of your soil test or just wherever, but I'm assuming or pretending that I've got 1,800 ppms of calcium, 300 ppms of magnesium, 130 potassium, and 48 of sodium. Then I take my milliequivalents per 100 grams from our last chart and divide that into the ppms, and I get these milliequivalents per gram oven-dried soil over here. 9, 2.5, 0.33, and 0.2. So that's all pretty simple. You add those up, 9 plus 2.5 plus 0.33 plus 0.2, and that's going to give us a CEC of 12.03 for our base cations. So that's our base cation CEC is 12.03. So now we have to do the acid side of this. You know, we talked about that exchangeable acidity earlier, and we're not going to add that up the same way we did with the basic cations. We're going to do this a little bit differently. So they're going to use a buffer pH. And so you've got your acid cations, hydrogen, aluminum, ammonium, iron, manganese, whatever. We need to know what our buffer pH is. And we're going to subtract that from 7. And I'm not smart enough to know how they came up with this conversion equation, but this is the conversion equation we use. And so we simply take our buffer, subtract it from neutral, which is 7.0, 6.6, and then multiply that by 12, and that gives us our conversion into our mechs per 100 grams of soil, just like it did with our base cations, but it's a different formula for that. And so that comes out at 4.8. Again, I'm not sure how they came up with that conversion equation. I'd have to do some research, but I just use it. So if obviously because 7 is what we're subtracting from, neutral pH is what we're subtracting from. So if your pH of your buffer is going to be higher than 7, or you have no exchangeable acidity, so there'd be no metric there, and so your CEC would just be base cations. So if that was the case, we would just have what was it, 12.03 would be our base cation saturation, and it would be our CEC as well. If we add these two together, though, for this example where we have an acid of 4.8, we would add the 12.03, our base cations, plus our 4.8 of our acidic cations, and we would come up with 16.83 mEq per 100 grams of soil, and that is our CEC. That's our, let me move up here just a second. So if you want to take a look at, so that's our base and acid, and so if you want to take a look at just calcium saturation, for example, you can take your calcium, your milliequivalents per 100 grams of oven dried soil. You can take this number and you can divide it by your CEC, which in this case would be 16.83. So we would just divide 9 by 16.83 times 100, and that gives us 53.5% calcium saturation. And that informs us to our other cations. And if we were looking at magnesium, what was that metric? That metric was 2.5. So we would take 2.5, divide that by our CEC, again 16.83, and multiply that by 100, and that would give us 14.8% magnesium saturation, and so on. So that's pretty easy to do. And so that gives you a really simple example, really fast, of how you would figure out your cation exchange, your base saturation, your acid saturation, and hopefully some relationships. And so if this is completely confusing, don't worry, you're never going to have to do this. It's already on your soil reports, but hopefully this kind of demystifies it a little bit, shows you what's going on at the lab. Even if you didn't catch it this first time, I guarantee if you slowed it down and took another look, or maybe two, you'd be able to follow along with this. Otherwise, I'm a really bad instructor, and my apologies. But take heart, you'll never be responsible for this number, and so hopefully we've exposed another layer of understanding, and you can use that as a tool to help guide your cultivation. So see you next Tuesday for the live. Tad is back, and hopefully he's got some tales from the road. I'll be putting out another Wednesday IPM and another Thursday Soil Tech video. So thanks for looking. Be good, and I appreciate you. Take care. Peace.